Hi, this is Mohammed. Now I was going to explain big data analytics and applications ICP8. So the main objective of this ICP is I need to generate some sample data from the data set. So my data should be similar to that of the input data. So actually my ICP suggests I need to add two more total 4 layers from into the source code, 2 layers in the encoder path and the 2 layers in the decoder path. So actually what is encoder? Encoder means will be the output that is generated should be same as the input data. The input data having the same distribution, but there will be some loss when it is encoded. Okay, so let me share my screen. Okay, this is the actual code. So here the first step, what I will be doing, I will be importing the libraries, whatever the required libraries will be using. I had imported here Keras, TensorFlow, and then the layers from the Keras and Keras model. So I will be using the pre-built dataset from the library Keras.dataset. So this is the data MNIST is the data I will be using here. Similarly, I will be using the NumPy as an NP and then plot for plotting the data. So here what I'll be doing, I'll be loading the data in. So this is the default data, so it will be split into training and testing. So the training, this is the training images, and then this is the training labels, the testing images, and this will be the testing images. So actually this is the supervised data, but we need to use only unsupervised data. So AutoEncoder will works only on the unsupervised data, but anyhow will be not using any of the labels. So we'll be getting rid of this label. So here I was printing the data size, the data shape. Here you can see the input train is having 60,000 images with the size as 28 by 28. And then the training data, and then the testing data is the 10,000 images with the size having 28 by 28. And then these are the labels. So actually when I was executing the data, so my system will run out of the memory, as because as this is the huge data, so it will run out of the memory. So what I will be doing is I will be taking the less data from the actual data. So here you can see I will be taking the 10,000 images as the training data and the 1,000 images from 10,000 images as a testing data. So next what I will be doing, I will be printing the first 10 images from the training data. So here you can see these are the 10 images in the 2-dimensional format in the X and Y label here. So then I was printing the reduced data set size. So here you can see, as I told, I had to 10,000 images is the training data and 1,000 images is the testing data. So here you can see the shape. And right now my next step will be I'll be adding the configurations to my model. So here are the specifications. You can see the image width and image height as 28 by 28. Input train.shape, and this is the index, so we'll be having 28 as the image width and 28 the image height. So then the batch size I will be using 128, and the approaches I will be using 50. Validation split is equal to 0.20% data will be used for validation. The remaining 80% will be used for the training. And so here you can see verbosity equal to 1 is nothing but a flag where whatever the output will be getting, it will be displaying on the screen. And the latent dimension is equal to 2. As I said, this is the two-dimensional data. Two-dimensional data, it will be plotted in X and Y labels. So the number of channels is equal to 1. As this is a grayscale data, so the channels for this data will be 1. And then now the next step will be, so actually the image size, it will be in the range is like 255 like that. So but our model will not work appropriately when the image size is higher. So what I will be doing is I will be reshaping the data. I mean, I will be vectorizing the data. To do this, I will be using the normalization. So here you can see, firstly I will be reshaping the data, and then I will be passing the numbers as floats, and finally I was normalizing the data. So here you can see I'll be dividing the images size by 255, so that my data will be my image size will be in the form of 0, and it will be in the range 0 to 1. So finally my data is scaled here. So, and then now I was creating the encoder. So here you can see this is the encoder definition. So this is the input function. So here you can see, so the input shape, as I told, it will be a 28 by 28 with the 28 by 20 with filter is equal to 1. This is the grayscale data. The name I had given as encoder input. So and next I will be adding the my model will be learning the convolution 2D layers along with the batch normalization. So here you can see the filters. The filters will be having 8 with this kernel size as 3. I mean, that means it will the 8 filters with 3 by 3 sizes, and the strides equal to 2. The skipping one position, and the padding will be the same, and the activation is equal to relu. You will be using the relu function here. So similarly, I will be using another layer for the another layer for this model convolution 2D with filter size equal to 16, and the image and filter 16 filters with the size 3 by 3. So here you can see actually in my source code we will be having only 2 layers, but as per the ICP suggests that I need to add 2 more layers in the encoder path. So these are the 2 layers I will be adding here. The filter size filter equal to 30 and filter 64. These are the 2 layers I will be adding here. With the same, my model will be learning the batch normalization. So when I will be adding the more layers, my model will be learning into a more deeper patterns, and then it becomes more complex for that model to be trained, so that it will be producing the accurate results. So and then finally whatever the data will be getting, so it will be in the form of like some multi-dimensional. So here I will be flattening that data, so it forms into a one-dimensional data, and then my data, my model will be learning the dense layers, and then again the batch normalization is performed here, and finally 2 more layers like mu and sigma. These are the 2 layers we will be building here through the dense layers. And then here what I will be doing, so when my data will be getting into size after performing the convolution layer, after training with the layers convolution to do with batch normal along with the batch normalization. So to get the actual shape, for it need to be given to the decoder set, right? So that's decoder. So that's why I was taking the actual shape here. So 7764, and then here I was defining the sample with the reparameterization trick. So here I was defining one function, a sample G, where this is a one more layer which will be added to the encoder path. So here you can see this is the one more layer where we'll be adding here. So here we have defined the function with the parameters, and then here we'll be calling this function as this will be working as a one layer to the encoder. So next we will be encoder instantiation. So here you can see our encoder will be trained, and then this is the summary you can see. So whatever I will be adding the layers. So here you can see the 28 the convolution, it will be reduced to 14 14, and then 7 7, like that. And then finally the next step will be we need to decode the same data, so that it should generate the sample data as the output, which is similar to the inputs. So here I'll be creating the decoder. So this is the decoder definition. The decoder definition will be exactly opposite to that of the encoder. Here you can see the input shape in the latent dimension, whatever we'll be getting finally here. So we'll be adding the input the shape latent dimension equal to 2. So here the same we'll be adding here the input shape you had given, and then the dense layer, our model will be learning the dense layer along with the batch normalization, and we'll be getting we need to get the same shape as that of the encoder. So actually see here, whenever we'll be using convolution 2D, our model is like 14 is 7764. To get into that encoder, we'll be using this function reshape. So that my images, my data will be getting into that shape, and then again I will be and then next I will be using the convolution 2D tempo, which the data will be trained into deeper layers along with the batch normalization. So two more layers. This is the two more layers will be adding the decoder, so which is exactly opposite to that of the encoder. So that he next. So in this way, I had added the two more new layers, and then finally my data should look like it should be in the form of 28 by 28 with one channel, right? So this is finally my data, the number of channels as I defined at the starting channel should be one. So in this way my data will be generated. So then next what I will be training this decoder, and this decoder, this is the decoder summary. Here you can see here you can 28 So as I said, when we are reshaping, our data should be in the size of 7764. Here you can see in the encoder 7764 the exact shape we need to get here 7764, and the initial in encoder the initial shape is 28 and here you can see the final shape 28 and finally we'll be creating the variation autoencoder is nothing but here it is similar to that of the encoder where the original inputs are encoded by the encoder and the decoded by the decoder. So here I'm instantiating the VAE, and here you can see the VAE summary, which where we'll be having the mu and the sigma layers. And finally, I will be compiling my model with the optimizer equal to atom, and then loss function as a binary cross entropy. And then here I will be training my model. Finally, you can see the loss function. The loss function value is 0.1907. When in the source code, you can see the loss function is 0.1971, I guess. 0.1971 when we are using the two layers. So again, when we are adding the extra two more layers for the encoder and the decoder, here you can see there is a loss in the there is a decrease in the loss. So finally we can say that our model is getting improved. So whenever we'll be adding more layers, the model will be trained accurately, and it will train into deeper patterns. So finally I was plotting that data here you can see. So here I will be using two different two functions, which latent space, the parameters encoded data, and then one more function which underscore decoded the parameters are encoded decoded data. And finally plotting these data. So here you can see the number, these are the generated. So this with the blue color will be the number ones, and then someone when the color is in between the green and then dark blue, you can see two, like then 9 will be the yellow colors. So these are the data that was generated from the input. This is the output data which is generated from the input. So here you can see in the graph. Okay, thank you guys.